Good morning, grade 10s. Today we are going to be starting a new chapter called Solid Geometry. And in this chapter we are going to look at how to calculate the true length or the true inclination of a shape. Now, that's all very new words and it's all very confusing, but I'm going to go through it step by step with you guys.
So, as I've said, today we will start with a new chapter called Descriptive Geometry. Now, let's take a look at what this is. So, what is descriptive geometry? Descriptive geometry is a branch of geometry which allows the representation of three-dimensional objects in two dimensions by using a specific set of procedures. This means we will be using a piece of paper to represent and draw three-dimensional objects, and we can show different views in two dimensions. The resulting techniques are important for engineering, architecture, design, and in art. What this entails is that this technique can be used across different types of professions. And for those of you who are interested in these professions, this would be a key chapter for you to excel in. Now that we know the overview of the chapter, we can take a look at specific work we will be doing. We will take a look at transition or transformation pieces. So these are adjustment pieces between two shapes or a shape of a different sizes. Now let's take a look at what a transition piece would look like in real life. We have an example here of a hopper, of a funnel, a cone, and two examples of a gutter. As you can see, the hopper is the same shape, but it's two different sizes connected in one. The same can be said for the funnel and the cone. But the gutter here, you can see a change of the shape, and here you can see two shapes that is connecting into one new shape. Now we all know the form of the cone. So let's take a look at that. It is a representation of a small circle connecting with a bigger circle. So with descriptive geometry, we would have to draw a 2D representation of this 3D object. Drawing 3D objects with 2D views is also known as orthographic projection, which we have covered before. On the left-hand side, we see a 3D representation of the object in question. And on the right-hand side, we have the orthographic projection, which consists of a top view, of a front view, and a right side view. This part of the chapter you have covered before, starting from grade 8, and hopefully you still remember this. But this is not where our topic ends. The main focus of this topic is not just to draw a 3D object or shape into a 2D plane, but rather what it would look like if we cut this object open and lay it flat on a piece of paper. Let's take a look at an example of a cone. On the left-hand side, you can see a 3D representation of the cone. Now imagine there is a seam here on the one side of the cone that is used to cut it open. Now when we've cut it open, we open it completely and lay it flat on a piece of paper. When you cut this shape open, it will look like the picture given to us here on the right-hand side. Here we have a bunch of different shapes that have been opened up into a 2D form. If we take each of these forms, cut them out, and then we will be able to fold it to create the perfect shape it represents. Some of you may remember doing this in primary school or in kindergarten, specifically with the cube shape. Now you all might be asking, why are we doing this? Why do we need to know what the shape would look like if we open it up? Well, when it comes to a manufacturing perspective, each of these shapes first have to be measured like this in the 2D form, so that the production teams would know how much material needs to be used for each shape to create these shapes. At the end of the cutting process of the manufacturing team, they would then fold or fix it into the correct shape that it represents. Now let's take a look at what you will be doing here in EGD for this topic. Here we have a 3D model of a hopper. On the top right corner, you can see the 3D representation. On the left-hand side, you can see a front view and a top view of this hopper. This will be needed to find the true length of the entire shape to create a transformation that is seen on the right bottom corner over here. So this is what the shape will look like if you cut it open here on this seam, which would be the back seam over here, and then fold it completely open. Now, don't worry, this is a very advanced sketch that you will only be doing in the 11th grade. This is just to give you an idea where you will be working towards. So for us to be able to draw a complex drawing like this, we will have to go to the basics. The first thing we'll be looking at is how to get the true length of a shape or of a line, specific line. So what is the true length? It is any distance between points that is not foreshortened by the view type. These are all bunch of big words. What this means is that sometimes when you look at an object, let's say from the front view, it can be shown shorter than what it really is. So let's take this example here. Here I have a highlighter in my hand. If I hold it like this, it is seen as a step. But from the front view, you can see it. From the top view, you cannot see it. So from the top view, you cannot find the true length of the shape. Now let's say it's at an inclination. This would be the front view, and this would be your side view. As you can see here on the side view, it looks a lot shorter than it is from the front view. And the same can be said for the top view. It is a different length. So now we have to find out what is this specific true length of this highlighter. There are a few methods and a few rules that we will be covering now.
So, to find the true length, the true inclination of a form, we would have to look at 3 rules. The first rule would be, if one line is parallel to the xy line, that would mean the other view, the line on the other view, would be its true length. So then we would just take our ruler, and it would be 55 millimeters. Remember, EGD is always measured in millimeters. And then for the true inclination, just find xy line, just make it perpendicular. And then we just take our compass and we would mark out the angle from the xy line. Right, the second rule, if the line is perpendicular to the xy line, the top view would just be a dot. So that would mean the line given to us would be our true length, and the true inclination would be 90 degrees. Now we have a third rule. If neither line is perpendicular or parallel to the xy line, we will have to make one of them perpendicular. So I'm going to take my compass. I am choosing to put the sharp end on point A and my pencil on point B, and I will draw an arch upwards until I have a perpendicular line. From there, I will project this line upwards until it is the same height as the original point B on the front view. So it would be right over there. Then I draw a new line from point A to point B. And that line will then be used as my true length and true inclination. Remember, if you decide to put your sharp point of your sharp point of your compass on point A, that means point A would be the one that doesn't move. So point A is from where I will draw my line.